audio, I think.
Yeah, the audio got lost. Okay, so now can you see and hear?
Yes, I can. Can you hear me?
Okay. Yes, I hear you. Okay, so
perfect.
I can begin.
Yes, you can.
I just want to thank you so much for the opportunity. And I think the previous talks laid a very nice groundwork for me. Thank you very much for that. I hope it's a relaxing talk. I haven't made it very complicated. I want to talk to you about PET, but not applied to medicine as normal, but to minerals. We are calling it MinPET, and it's about the 4IR stuff, buzzword, tech transfer, innovation, commercialization. And I wanted to introduce you to diamond mining, where you have a lot of rock. And then, just hang on, folks, softer there, close the door. Excuse me. So you want to find that one rock which has the diamond in. So you want to sort barren from diamondiferous rock in an online run-of-mine, several hundred tons an hour method. So this is in fact the extreme case of something very high value buried in waste. And you can see that from the numbers. So just to take you on a little journey, you know, diamonds had their genesis about 2 billion years ago, typically, and then a partial extrusion till about 100 kilometers depth, where they lay till about 60 million years ago. So they recorded the continental drift and so on, and then in a violent event of a volcano, they came out. And the solidified lava is known as kimberlite, after the town of Kimberley, where the first properly identified volcanic pipe containing diamonds was found, now the mine of Kimberley. And then we can look back in history and see when was there first evidence of diamonds for early hominids, and that is now being dated to 4,500 BC, because China, they have archaeological relics which are axes made of corundum with a hole in, therefore implying would have to have been made by diamond. And if we go a little later, we see there was the concept of kimberlite pipes, not so called, but there would have been pits eroded because kimberlite is soft. And then in the bottom of the pits, they would lay diamonds, and there were snakes in the bottom of the pits, as you see in this ancient woodcut. And the way they mined them was to throw meat down, and eagles would go down and get the meat. And because diamond is hydrophobic, it would stick to the meat. And the eagles would carry it back up to the surface. They'd extract the diamonds from the eagle droppings. So that's a nice historical introduction. And now I want to go over to our group, which has a program at CERN, and the things I'm going to show you we learned at CERN. For example, sensor development, simulation, high data throughput, big data analysis, high performance computing, high level human resources, machine learning. And so this is a kind of a tech transfer project. So we first start with the idea. You've seen what PET is, but we want to cancel out where you inject a patient with a biomolecule labeled with some radiological isotope. And instead, we want to use a giant dipole resonance, a gamma-N reaction, where the gammas are about 20 onwards MeV, and do a transmutation. We're going to do it on carbon. The carbon-12 will become carbon-11. That will give us our PET emitter. And then we want to use this activation technique or transmutation technique to activate just the diamonds inside of rock. And I just gave you this picture because it's quite awesome and shocking. You can see on the surface of the pit skyscrapers. And so you can really get an idea how big this pit is. It's the biggest in the world, Murny diamond mine in Russia. And I want to say it's mined out. You look at the whole world and you find 50 diamond mines, and it's all surveyed. Aircraft have flown everywhere. All kimberlite pipes are believed to have been identified. That means 6,000. 1% are commercial, leading to around 50 diamond mines, mostly concentrated in Africa. How do they extract the diamonds? Well, they've got to process all that rock. They crush it, basically. You see crushers, you see a grease table not far away from that piece of meat that got thrown down the pit some 1,000 years ago. So there's still a grease table in action nowadays, but breaks diamonds. Here you see 4 stones from the Cullinan. It's about 10 years ago. It's the first time they installed sensor-based sorting. So De Beers owned the Cullinan. They sold it to Petra Diamond. Younger people introduced modern technology. And it's a XRF technique that they used and could make diamonds falling in a chute glow and use photodiodes to recognize that. They could only spot liberated or exposed diamonds, but these 4 were pulled out within 1 minute of each other. Now they should come statistically on average 2 months from each other. So when 4 come in 1 minute, they were the same stone. It means it got crushed, but you cannot piece those ones together. So there's more material that you didn't recover. Now look at these 2. It's 2 pieces. You can see how they fit together. I saw Krish in the audience, so he will also recognize a stippled surface uppermost and facing towards us a cleaved surface. So you already see that this is not all that nature had. How big are diamonds really in nature? That would be very interesting. So what you can see is these sold, the small one for $200,000 and the bigger one for $7 million. But the estimate, if they were not broken, just those 2 pieces joined together, an extra $10 million. The whole lot's going to pay for your sensor-based sorting. Now, if we take a look at the Cullinan diamond, that's the world's biggest, 3,107 carats. The face on the right is the stippled one, and the face on the left behind that you normally don't see, that's the cleaved one. So it leads you to guess, well, how big was the Cullinan? Was it twice as big? So MinPET in a nutshell, what we want to do is take a rock stream. I'm going to show you with my pointer. There's a coarse crush only. And from this rock stream, you'll go into an irradiation hopper. You'll have a system that can illuminate this with 20 to 40, 50 MeV photons. So you need a photon source, very strong. And you will irradiate the rock and you will activate the carbon in the rock. Then you have a hold hopper, because the lifetime of that PET isotope is 20 minutes. You let everything else decay out. It's practically only carbon left when you come out this chute. I mean, carbon isotope, PET isotope. So it's actually very quiet, the rock, by this stage. You can practically stand next to the belt. And it's literally only got the carbon PET activity. And you have a linear PET array, and from that you reconstruct your geometry, and then you can process that with a classifier, and you can talk to an injection system. Okay, so schematically, it will look like this. There's a rock, it's got a diamond in, it's the most PET active thing. But actually, you need millions of these lines of response, as is shown here. You see really a point source, and then you can see how many lines of response you need. Here, I just wanted to show you that if you wait 60 minutes, then you can compare the activated signal to a one that had not been activated. And if you compare peak for peak, you're going to see a very, very, very little difference, except for the 511s. And you can really see the 511 activity is the most activity. So somehow it works out that PET is the most important thing here. There's a sodium 24. You will recognize 15 hours. That becomes the dominant background, but it also decays away. And then you already see the potassium 40, folks, you'll recognize. So the very first experiment was in a medical facility. This is in Karolinska Hospital. It's got associated a physics department that does medical physics. That's Bengt Lindgren, who is from their medical physics department. And we booked time on it like a patient. So our patient was a rock with a diamond spiked in. And then we carried it from there, and I really want to emphasize that it wasn't very hot. And we put it in their own PET machine in the same hospital. And there you see the picture. So you already on this unoptimized scenario, you see that PET can show a diamond in a rock sticking out like a sore thumb. Why is there purple for the rock? That's because of carbonates. About 5% of kimberlite up to can be carbonates. So what you're really seeing is a 3D image of the distribution of PET isotopes, of which, because we waited that 20 minutes, 13 minutes, the dominant one is carbon. There's also some oxygen there. And but you see the homogeneous distribution of carbon from the carbonates. This is because the kimberlite rock was molten and everything got mixed up and pulverized except the diamond. So diamond remains as a hot spot in a carbon background. So now we've done also a lot of detector development. So we are going towards PET detectors that are really for mineral PET, not for any other application. And we've also gone to silicon photomultipliers and very high performance electronics, putting intelligence right up at the very front. The biggest chip you see there in the middle is actually a FPGA, and it's assembling the event. And then there's lots of other little twiddles to allow us to handle a very, very high data rate. And this is the team I want to give credit to, Net Instruments. It's a spin-off. We had been working with them a lot in nuclear physics. Even at Itemba Labs, they have built machine preamplifiers and so on for Itemba Labs. In Itemba Lab, colleagues may recognize some of them. So now what does it look like? I want to flash through, okay, because these are images that when you show them to a diamond miner, they go absolutely nuts. So there is no competitive technology that comes anywhere close. So this is now a rock of 10 centimeters side, mainly governed by you want to get the PET activity out and spiking diamonds inside. You see it stick out. That you get a three-dimensional thing is because of this. It's elongated because we have a linear PET array. It's not the circular one that you're accustomed to. But you see very, very clearly the diamond in the rock. And here you see in this picture that you can have slices and you can recover it. And there's a lot of artifacts here that wouldn't be in another system because it's to do with the fact that we did not have a homogeneous beam. It's still sticking out. Now, we have been talking a lot to industry, and you can have alluvial deposits. So for example, you can imagine a very ancient kimberlite pipe weathered away, and then a riverbed should have the diamonds like the Orange River for us, or also at Namibia and the Orange River mouth, a lot of diamonds deposited there. Then they will be with calcium carbonate. Now, if we look at doing PET here, if you come with your gamma N reaction, you're going to by hook and by crook. You know, there's lots of parents and daughters and granddaughters and so on, and you are actually going to make potassium 38 PET isotope, you make oxygen 15, and then you're going to have carbon 11 from the carbonate, because in carbonate. So we said, no folks, we are not going to manage to see a diamond in a calcium carbonate sedimentary rock, but we did. So it was very interesting, and this is not on a very high resolution PET system, but you can already start to see some mineralization. I think there's a 3D picture of it. Because this rock is not kimberlite, it's not homogeneous, so you start to see structure because of the other components in the rock. And so now let's go smaller. So this is a smaller piece sticking out more like a sore thumb. How small could we go? This is a 0.2 carat diamond in that rock. Go to a cylindrical symmetry, and then you have less artifacts. So this you see more clearly. Here's a bigger one, 18 centimeters. And you see a diamond in, this is an oddly shaped one, just less than a carat, and you see the diamond in. So these are typical pictures. And now I just wanted to touch base a bit. We heard about Giant 4. So we do the full sim with Giant 4. So we start the sim with this electron accelerator, and then we have a bremsstrahlung target, and then we develop the mixed radiation field through all the rock in the irradiation chute. We treat the nuclear physics from the Tyndall database, and we look for the GDR that I mentioned before. And then we follow other channels as well. So there's another code that reactor physicists and reactor engineers use called PhysPact, if you're familiar with that. You can track every possible neutron-induced, photon-induced, alpha-induced, proton-induced reaction, and all its daughters, and do it in a time series, time differential, and so on. So we use this code to identify all reaction pathways. And we added this in, and then let's say you had a neutron flux from your gamma N, we could put this in as well. So now we also could simulate the moving rock stream. So with Giant, you have to do a separate run. So every time slice becomes a run. And then, depending what we want to do, we could actually follow recoils and look at recoils in diamond. So for example, if you did gamma N on a carbon, then that carbon 11 is actually going to recoil off, and it will cause damage, and so on. Then a secondary damage and from the neutron flux and so on. So we looked at the damage in diamond. You can imagine that no one wants to recover diamond from a technique which actually damages it. I want to say a bit about that. We also looked at the activation of kimberlite, and we did a lot of benchmarking there between Giant and experiment. And then also we simulate the detector response, and we produce data into pulls. And at this point, very much like Dan's talk, we could feed sim data into the next part, or experimental data. So they're the same format. And then from that, we could go to 4D sonograms or 3D reconstructions, and we could put the AI on that. So this was the technology to use large-scale sim to train the AI. And so this whole process in this picture is all simmed. And here's just a separate sim, just developing a mixed radiation flux in a bremsstrahlung target and going directly into diamond and tracking these recoils. This is now asking Giant just to histogram the paths of the recoils. The beam is coming from the bottom, and you can see the little tendrils here from this sim on the left. And from that sim, we looked at the formation of the single vacancy, which is the GR1s, the primary radiation-induced defects under a part per billion. Here we compare the diamond living for 2 billion years, half the age of the Earth after its genesis in the crust of the Earth, okay? And there it's with the potassium-40 and the U-235 and the thorium-232 and so on. And so that diamond is in any way getting irradiated by Mother Earth, from which we could conclude that there were 10 to the 4 orders of magnitude more irradiation and damage on the diamond by nature than by the MinPET recovery technique. I've basically summarized so much research in a few slides. For the SIM, there's this huge effort to benchmark it to experiment, lots of little bits and pieces. And using high performance computing and getting very, very large data sets. And we managed to take the computation time down from detection to 5 seconds when we have the classification. And then also a scale-up tool. So here you see an actual belt. It's exactly the size it should be. On the right-hand side there, folks, it's the actual conveyor belt and detectors and some events. And so that is a full-scale SIM. And we use that to do scale-up studies. We have a full dress rehearsal, we call it, but it's lab scale. The full dress rehearsal literally means, like for me now, when my grandchild would do a play, then they could do it, you know, act 1 on its own, act 2 on its own, not be in their costumes and so on. But when you put all the bits and pieces together, so you have them feeding each other and they all integrated. So you have activation and you have hold hopper and you have your transport system and you have your detector array and you go all the way through with the whole system. It's the full dress rehearsal. We compare at that stage SIM and experiment, carefully benchmarked SIM. And, you know, like Donald Rumsfeld, the known unknowns and the unknown unknowns, no one knows what are those unknown unknowns. So I should just say we do in physics because we can SIM. And when we trust the SIM and the experiment and the SIM agree, then in the disagreement, that's the last surviving place for those unknown unknowns. And that's a very interesting concept. Now, what about data rates? So we've been very fortunate. We've always had a colleague in the Atlas TDAC. And so we've always known how are they doing it. And we have a copy of that. But how do you implement it in MinPET? And so we have a way to segment a moving belt in moving baskets that pass their ID over and to different sub-networks. And in that way, split the data and then separately produce these 4D sinusoids that schematically we're showing here. And then recombine them once the data is highly compressed. And then you have many, many computers that can do this, the data splitting into regions of interest. So it's this concept of regions of interest that's over here. So Atlas does it with 160 gigabytes, and we are doing it with 16 gigabytes. I don't want to say too much about the commercialization part, so I'm just using the annual report of gem diamonds. This is the producer of large diamonds. As a diamond mine is called Letseng in Lesotho. This diamond mine produced these diamonds that you see down here, very, very big ones, very, very clear ones, very, very high value ones, all broken. And so the biggest business case really is to go to Letseng. And we have had a wonderful relationship with them. So here I wanted to show you, just break from that a bit, but show you some more ideas. So I can only show you this now, it's only free to show you now, but what you are seeing is a time differential PET, and then analyzing the time differential signal to give element sensitivity. So we're calling it PolyPET, it's an element sensitive PET. And then you see here plotted what it would look like if you would analyze explosives, narcotics, or plastic, and you can separate them. So one low-hanging fruit now that we are going for is coal, using carbon as a proxy for calorific value and oxygen as a proxy for moisture content, and do online real-time coal. This is a typical thing here. You see a time differential spectrum on your left, and that's a 511, and inside it is the decays. And then you know how to segment, because you're only going for certain isotopes, major elements that you know to be there. So you can relatively quickly pull these things out, and then you can imagine technology where you would extract 3 kilogram samples every 5 minutes, and then have a PET activation and scanning system. And we're also looking at our detectors in this context. This is a total body PET or something. So at the moment, there's a machine called the Human Explorer, and it's not yet taking full advantage of all the tricks that you can do to really have a very correlated detector system. And our detector system is optimized to correlate each and every pixel. So it handles the high data rate because of that. So we also want to look at this total body PET, but it means you can do a lot more. For example, in the case of Explorer, they have shown that they can be 40 times more efficient with their first off version of a total body PET scanner. So you could do lower dose scans, multiple scans, time variation, PET video, and dynamics, and so on. So those are the things. So now I'm really coming to the end. I want to talk to the students. If you are interested, folks, you are absolutely welcome. So on the red, you see that there is fundamental research. So in our case, there's dark matter, for example. But you learn a lot of tricks, and so you can add an idea. And from there goes to disclosure to the tech transfer office, and then protection of the IP. And we have put 11 patents, of which students have also been part to these. And hopefully students also will benefit from doing that. Sometimes you may use secrecy. In our detector, a lot is actually done with secrecy. And then you could be exposed to other things. So if you have the appetite, folks, if you like to, there could be exposure to market research, economic modeling, building a business case, integrate the device in a plant, benchmark competitor technologies. We sim them too. We take them apart. Fundraising and prototype development. There's lots of fun there. Technology readiness levels, scale up. And then, you know, it's like our own little soap opera. We have legal issues and various impediments. Very fun story. I'm looking forward to telling that once it's all done. And then we talk to CEOs of companies, we talk to venture capitalists, we talk to technology partners, and we talk to customers. So I wanted to say, students, please look at our website, look at the opportunities. There's always opportunities. Please contact me through that website. Now, Nico has at the bottom of his email about Spartans. So Nico, I want to show you the Zulu warrior, where the warriors of the Zulu impi called out to the young men, grow up to be yet braver than we. So thank you, Nico, for this opportunity. Thank you all for listening. And I just leave you with this list of icons.
Thank you very much, Simon. And thank you to the two speakers before that as well. So Simon, you had a couple of comments in the chat. There is a lot of interest. David, if you would like to comment on your comment. So Simon, you were already interested in the PET using the quantum entanglement. So there will be another talk from Ruth from York after the break. And David?
Yeah, I mean, maybe this is a slightly premature comment because you haven't seen Ruth's talk and other people haven't seen that yet. But I think one of the very interesting aspects of this quantum entangled PET, which really is a simulation based at the moment, is the possibility to reduce scattering background. And for the medical things, that's less important, but we'd been thinking about industrial applications, and we were thinking more like big lumps of metal or something, and being able to image in a very lossy way. But it seems like what you're achieving is definitely in that category. So it might be very interesting to talk at some stage about that to see whether it's something we could look at.
Definitely we do that. I think that was one of Nico's goals, right?
Yeah.
So that would be fantastic. Thank you.
Alejandro, a question?
Yes, Simon, was a fantastic talk. I have a question. How competitive will be your PolyPET compared to neutron activation, for example?
Yeah, so I think in the first case, neutron activation is not going to do carbon and oxygen. You could do that with elastic neutron scattering. I think there's the appetite in the industry is to rather not have neutrons. And I think when I look at how to really get a 3D information from the neutron technique is very difficult. So I don't know, it will be if this coal analysis or PolyPET, it really wants to exploit the 3D, because that's what PET can bring you. We've looked at 2D PET, and 1D PET, and you can go to cheaper, simpler, faster detectors if we drop the number of Ds. But once we start to drop the number of Ds, then I think the neutron techniques are going to get more competitive. So I think that this we are starting now to look at. So for example, wet coal is a very, very important. In South Africa, we have a lot of coal. Okay, coal-fired power stations. I know we won't. Let's say 20 years time, we won't. But now we do. And so now our electricity supply utility, Eskom, is very keen to know the moisture content of the coal. And so there can be a case there for the 3D, because then you really want to look through the coal and see. So we'd be able to image each piece of coal. Then there's been fraud where people put something like it could put some oil on the coal to increase its calorific value, when actually it's mostly, let me say, sand. And so those kind of things could also be diagnosed because of the 3D. So I think we plan to start. So in fact, we start very, very soon to look at this in the coal context, as PolyPET in the coal context, and see if it was looking for landmines, or we were also hearing about homeland security, the borders and so on. I think, you know, we got the range of the 500 keV coming out. So we could activate the ground, for example, with landmines. So we also have this as a proposal, but I would say we haven't done much work on it, but it's a proposal that you activate the ground. You could activate to, let's say, 30, 40 centimeters, maybe a bit more. And so if there was a landmine buried that deep, then you would have a PET isotope down there. And then you would use SPECT, the gamma camera, the 2D version, because you can't put a detector underneath the landmine. So you would image with a SPECT camera. And so those are all different things. So I think, I mean, we need more piston power, and then we would start shunting those scenarios and just seeing how competitive PolyPET could be there.
Thank you. Tom, is there a question?
Yeah, thanks. So hi, Simon. I think it's such an ambitious use of nuclear technology in an applied space. I'm wondering, what's the drive for imaging the diamonds directly? You've got all these problems with attenuation, correction, and self-absorption. Just in terms of detecting them, it seems that it would be a lot easier to use, as you say, less Ds. But what's the drive to image them?
There are things that can also masquerade. There can be wood, there can be rubber in the rock stream. The diamonds are very, very rare. To get to see down to the smaller diamonds, you really need to see them in the carbon background of their own voxels. And you don't want to integrate the carbon background from wider ones. So it turns out the 3D is absolutely necessary in the diamond industry. And then there are a lot of ideas. For example, the people who do X-ray transmission, which is the closest competitor, they want one rock isolated presented to the scanner, okay? So they speed up the belt, and then the rocks, like traffic, separate. And then they have one rock at a time going on under the scanner. It's just like your baggage scanner at the airport, dual energy X-rays type of technology. And they can segment to diamond. But in our case, we do better when there's a bed. So I don't know if you've experienced of PET, you'll realize that the edge effects are your enemy. And so if you can settle the rock into a bed, then you start to do better. So we have to do a systematic correction for voids, basically, because the less scattering in a void, as you've just mentioned, the scatter problem, can actually look like more signal. And so there are those kind of systematics. And I think then the fact that PET likes a bed of rock, the opposite of XRT is giving it a rate advantage. And so it just seems very, very nice. But you can imagine, there's 1 carat per 100 tons. And I mean, you have to do a lot of rock. So you are lowering the energy and the water consumption, the carbon dioxide production, amount of plant, and then also the risk of breakage.
Simon, unfortunately, sorry, I was interrupting, okay. But we are too late today. We have been, so Nikita, thank you so much for your talk. I'm sorry, Nikita, I don't want to take over.
Okay, so thank you, Simon, and everybody. The next speaker is actually Tom, and we are already late for his talk. So I would like to give everybody a 5-minute break, just a quick bathroom or coffee break, and we'll get back in 5 minutes.
Thank you so much, Nikita.
Thank you, Nico.